Alright, pre-calculus students, welcome back. We have our next video in our conics section series, and we're moving on to hyperbolas. Alright, so we've covered circles, we've covered ellipses, and now we're going to get into hyperbolas. So, definition of a hyperbola. It should look pretty similar, but we're going to always start with the set of all points in a plane such that the difference between the distances to two fixed points that we call foci is constant. Alright, so the big difference here, the huge difference, the reason that this is not an ellipse is this word right here, difference. Okay? In an ellipse, it was the set of all points that the sums of the distances were constant. Now we're talking about the difference being constant, okay? So that is what makes a hyperbola a hyperbola. We need to understand now that we're not really going to be using major and minor axes anymore, okay? We change. We call them the transverse axis, the conjugate axis. Now the transverse axis is where everything's at, right? So we have the center goes through the transverse axis, and the vertices of the hyperbola go through the transverse axis, and the foci are located on the transverse axis, okay? So this would be our transverse axis right here, and hopefully you can see it's because all of this stuff is on that line, the x-axis in this case. Now the conjugate axis is the other one, if you want to think about it like that. Or what we really know is that the only thing that goes through it that we care about is the center. Alright, so here we go. In this case it's the y. This would be our conjugate axis. Okay? Okay. Now, hyperbolas can go in multiple directions, alright? Ellipses were pretty nice. We knew that just looking at the r sub x and the r sub y, we could tell which direction it was going to kind of be pulled towards. Hyperbolas are a little different, okay? So a hyperbola that goes along the x-axis, we would know that the vertices would be here, and I would kind of sketch something like this. The dashed lines are pretty important. Those are our asymptotes. Our hyperbola can never touch, it just approaches. So something like that. Well, that would be a hyperbola along the x-axis. We can also have them along the y-axis. So notice, nothing's changing, just where I'm putting my vertices, and now it opens up and down rather than left and right. Okay? So let's be really careful here. I should also make sure to say, here are my foci, and here are my foci. Just call this 1 and 2. Alright, so notice the difference, hopefully. In this picture, I'm not using my foci along the x-axis, even though there's kind of one there. Don't think about that one, okay? The foci are on the on the transverse axis. Okay, well, standard form. Again, should hopefully look fairly familiar. There's a major difference, though, that's going to give you a hint that you're working with a hyperbola. So if our hyperbola is going along the x-axis, then our x term comes first. X minus h squared over r sub x squared. Now here's the difference. Hyperbola, subtraction. Okay, in ellipse this was a plus sign. Hyperbola, minus sign. Y minus k squared all over r sub y squared equals 1. Excuse me. What's really great about this is, like, whichever one is positive, this defines the transverse axis, okay? So because this comes first, x is transverse. Okay? Well, if we have a hyperbola along the y-axis, what do you think is going to happen? It just switches. Alright, now we have y minus k squared over r sub y squared. And now it's minus x minus h squared over r sub x squared, and that's still equal to 1. Okay? So the only thing that's different between these two is the placement of the y and the x. Alright, so now we know that y is transverse. Okay. So when we come down here, there's still some more stuff. I know there's a lot, but the slopes. Okay, when we say slopes, we mean the slopes of the asymptotes. All right, and it's actually not too bad. We knew, regardless, r sub x and r sub y, like we know these distances. Same thing on the other picture. So we can just think about slope as change in y, change in x. So if I want to get to this point, excuse me, all I have to say is, well, I went up r sub y, I went over r sub x. Alright? So slope is just r sub y over r sub x. Now we need to be really careful, because there's two asymptotes. What would happen if I went down r sub y and over r sub x? Well, then I would have a negative slope. So the big idea here is that slope will always just be plus or minus, and then your r sub y over your r sub x. For the asymptotes, there's not like a surefire way to do this. You're going to have to use point slope form, excuse me. Okay, so you're going to have to use y minus y1 equals m x minus x1. Alright, and we'll see that in a little bit. For the focal radius, it's a little bit different, and this is where we don't say major and minor anymore. Okay, it's not major and minor. It's excuse me, transverse and conjugate. Okay, so what we do here, I don't know if you remember from the ellipse, but it was the major squared minus the minor squared. Well, everything seems to just be kind of flipping. So now we're just going to say r transverse plus r conj. All right. So that's pretty easy. And lastly, eccentricity, r sub f over, well, in an ellipse it was r sub f over r sub major. Now instead of saying r sub f over r sub major, we're going to say r sub f over r sub transverse. Okay? Okay. So if we do this, and we kind of think about this, this is always going to be positive and positive. So what's going to end up happening, guys, and I think I misspoke when some people asked me about this, our eccentricity for a hyperbola, eccentricity for hyperbola is always greater than 1. Always has to be greater than 1. That should make sense, because if you're taking two positive numbers, squaring them, and then you're going to square root it, right? But that number, when you square root it, is still going to be bigger than just this transverse, or our subtransverse, okay? So hopefully that makes sense. Our eccentricity for hyperbola should always be greater than 1. Alright, so now we have to put all this to work. Let's see what's going on here. Alright, so we have an equation in general form. We want to put it in standard form so that we can graph it. This looks pretty good to start. It doesn't look like we have to do any rearranging. I think the major thing we have to do here is we have to realize that this right side does not have a 1. So I'm going to need to divide by 144 everywhere. Alright, and when I do that, well, this cancels nicely, okay? So this is going to become x squared over 16, and then I'm going to have y squared over 9 equals 1. Alright, this is cool. This is good. Now we know some things. Well, we know that there's no h and k values, so our center is 0, 0. We know that r sub x is the square root of 16, or 4. R sub y is square root of 9, or 3. Very important here. It is not because r sub x is bigger that x is the transverse. X is going to be the transverse axis because it comes first. It's the positive piece in our form. Does that make sense? I really hope so. You're not looking for the biggest, you're looking for what comes first. Alright? So we know that our transverse axis is going to be x in this case. We know that our conjugate axis will be y. Last little thing we need here, plus or minus, remember it's change in y, change in x, right? So that's your hint that it's going to be the y over the x. So 3/4. Now we can kind of put all this together. Let's see what this is going to look like. Well, our center is at 0, 0, so we'll probably plot that. We need to make that box. I don't know if you remember it. We can go back to the first page. All of these, we draw this little dashed box. That's our next step. So, r sub x is 4. That means I need to go 4 to the right, 4 to the left, and I know that r sub y was 3, so 3 down, 3 up, and this defines the box. Now I can draw in my asymptotes, because my asymptotes just go through the opposite corners. So I could do something like this. And another one. Am I doing this right? Yeah. Alright, so those are my asymptotes, asymptotes, and then the big finish, okay? We need to remember that the vertices, or the direction of this hyperbola, goes with the transverse axis. We said that the transverse axis was the x-axis, which means my vertices are going to be along that axis, or right there. And that gives me my final shape. Okay, so there you have it. There is our first hyperbola. All right, vertices, we want to think about this as, well, we knew that, oh yeah. So we're going to take, for vertices, you're always going to take your center, and then add, subtract the correct radius. Alright, and what I mean by that is, in this situation, because the transverse axis was the x-axis, well then what's going to happen here is k is going to stay the same. But what I'm going to have to do is I'm going to have to take h, and I'm going to have to add or subtract r sub x. Hopefully that makes sense, right? We know that we're starting at the center, and because the vertices are going to the left, to the right and to the left, well, I just need to take away or add that radius. So in this situation, I had a 0 as my center point, my h, but now I'm adding or subtracting 4. So plus minus 4, comma 0. Asymptotes. This is a pretty easy example of asymptotes. More times than not, you're going to have to do a little bit more work than this. But again, you use point slope form. You need your center. and you need your slopes. Alright, so in this situation our center was 0, 0, so this is going to be nice. We're going to have y minus 0 equals, well, one of my slopes was positive 3/4. I guess I didn't need the plus sign, but 3/4 x minus 0. When I distribute everything, solve all that, I just get y is equal to 3/4 x. Alright, which actually then we can see, because our center is just 0, 0, we're going to end up getting that our second asymptote is nice and easy. It's just negative 3/4 x. You have to be careful though, guys. You need to do this in separate steps. If our center was not at 0, 0, you need to kind of recognize here that when you distribute and then you add or subtract, the values are not going to work nicely by just using plus minus 3/4. Okay? So you have to do two separate equations there. Alright, let's bring this home. Last page, almost there. Alright, so we have general form. Let's put this in standard form, okay? So this is completing the square. Hopefully we're getting pretty good at this. I know I'm going to have 9x squared plus 90x minus 4y squared plus 32y. And then that's going to equal negative 197. Alright, so this should look familiar. This is going to work very similarly to what we've been doing. Major difference, I have a negative 4, okay? So this is a hint that we're going to have a hyperbola rather than an ellipse. So let's factor this out. So 9, which means I'm going to have 9x squared plus 10x. I'm going to have to leave a blank. And then I'm going to have to subtract 4. And when I take out 4, I'm going to be left with y squared, and I'm actually going to be left with negative 8y. So be really careful, right? You have to make sure you take out the negative 4 from both. Then I'll leave a blank, equals negative 197 plus blank plus blank. Alright. So what gets filled in here? Well, half of 10 is 5. 5 squared is 25. Half of negative 8 is negative 4. Negative 4 squared is 16. But please remember, those are not the values that get put on the other side. We have to do 9 times 25, which is 225. And we actually have to do negative 4 times 16, which is negative 64. So that's a big deal. That's gonna look a little different than usual. Alright, let's see what happens here. We have 9. This is going to be x plus 5 squared. Then we have minus 4. Y minus 4 squared equals, alright, let's see here. What do we have? Negative 197 plus 225 is 28. 28 minus 64. What is that? 36? Negative 36. Oh, interesting. Okay, so not only is that not a 1, but it's also negative. So that's actually going to change things up quite a bit. When I divide everything by negative 36, what ends up happening here? Well, now I actually need to kind of flip these spots, right? So I'm going to clean this up. This will be a 1 and a 4. This will be a 1 and a 9. But you got to remember, now a negative divided by a negative is a positive. So these two places are actually flipping. The x is not the transverse. It's going to have to be the y. Alright. I hope you guys saw why that happened, right? A positive divided by a negative is a negative, right? So I needed to move this x term to the second piece because now the negative divided by the negative was the positive term, okay? Cool. Well, let's take a look, see what we've got. We know our center is going to be at negative 5, 4. That's still the same, right? H comma k. R sub x is still with the x term, so square root of 4 is 2. R sub y is square root of 9, or 3. Slope, y over x, 3 halves. I think we're about ready to graph this now. Let's do it. Well, if our center is negative 5/4, that means I have to come here and here. Alright, there's my center. I know my r sub x and r sub y, so I can go over 2's, up 3's, and I can make that box. Alright. That allows me to then create my asymptotes. See if I can get this. Yeah. Alright, there's one asymptote. Here is the other being sketched in now. Alright, and now we have to remember what was our transverse, okay? And I should have probably marked it earlier. The transverse comes from the first piece, or the positive term. So the y is our transverse, which means our vertex goes along the transverse axis, or the up and down axis here in this situation. So I would finish this by just sketching the hyperbolas that go sketching the hyperbolas that go with those asymptotes. Alright? So, last couple things we need to think about here. Length of transverse axis. Well, the transverse axis we said was the y piece, and if here's our center and we go up 3 or down 3, then the length of our transverse axis is just 6. Alright? Thinking the same way, but now with the conjugate axis, well, we went 2 to the right, 2 to the left, so our conjugate axis length is just 4. For vertices, we know, again, we start at the center, and we use that transverse axis to help us. We know that the vertices are going to have to be at -5 and -5. Why? Because they have to be along this transverse axis, and the transverse axis always has an x value of -5. But we need to use the fact that the transverse, or the r sub y, y radius was 3. That means we have to go 3 up from the center and 3 down from the center. So if we were at 4 and we go down 3, that would take us to 1. This is just 4 minus 3. And then we have 7, because 4 plus 3. Alright, and that is kind of how we think about that. Alright, lastly, the asymptotes. Here's where you have to do a little bit extra work, and this is a little more difficult than the ones before, so I think it'd be good to do. We know that we're going to use y minus, we're going to use our center point, so it's going to be y minus 4 equals, then we have to use our slope. So I'm going to use the positive first, and it's going to be x plus 5, something like that. So here's an example where you definitely need to distribute. So I'm going to have y minus 4 equals 3 halves x plus 15 halves. That looks good. Well, now we need to add 4. I would strongly encourage you just leaving it as a fraction, and remember that if you want to add 4, you can also kind of think about 4 as 8 over 2. So I'm going to add 8 over 2. So y equals 3 halves x plus 23 halves. Cool. That looks about right. And then we need to do this again, but with our negative slope. Alright, so we'll finish this up by doing y minus 4 equals negative 3 halves x plus 5. Let's see here, we get y minus 4 equals negative 3 halves x minus 15 halves. And once again, we're adding 8 halves. So negative 15 halves plus 8 halves should be negative 7 halves. And that looks about right, because negative 7 halves is about 3.5. And there we are on our graph. Okay? So, that is an intro to hyperbola. I hope you guys see the kind of comparisons with it to ellipses, and that you can really kind of focus in on those differences to make it not quite as difficult and not like a brand new idea. Alright, so there we have it. We'll work more on this in class. Have a great day.